Welding stainless steel has similar characteristics to carbon steel, but when welding stainless steel, it likes to trap heat and distort. You can control distortion by bracing the weld joint or spreading out your heat. You can brace the part by use of jig or clamps, or by placing a piece of wood or a bar between two sides to help it not close in. Another way to control distortion is by spreading out your heat, and you can do that by backstepping or staggering out your welds around the part, or simply waiting in between welds for the part to cool as well. The most common electrode used for this process is ER308L and uses carbon dioxide and argon mix shielding gas. You can also use GMAWP, which is sort of like spray transfer because the power source switches between peak current and background current from 30 to 400 times per second. This allows a droplet to be pinched off when the switch happens to the peak current. This allows the pool to freeze slightly and prevent burn through with a clean arc and minimal spatter. This will help with carbide precipitation when welding stainless steel and help control the heat with a softer arc, and a fluid weld pool allows for better tie-in to the base metal at the weld toes. You can also weld stainless steel with Fcaw, but there are many cons to that. Like, some of those cons would be risk of slag inclusions, and it's not going to be as strong as a TIG weld normally would be. And you would need to run it on electropositive, but some of the cheaper machines only run PCE. And here's a video of how pulse MIG on stainless steel will look like. As you can see, this is the arc characteristics of using pulse. And you can see it comes out with a smooth flat bead. As you can see, according to this picture right here that's provided to us by Lincoln Electric, the ER is going to stand for electro rod. The 70 is going to be your tensile strength. The S is that it's a solid wire. Is the X, or it's normally a number or a G, is going to be your added chemicals and cleaners to the metal, such as aluminum, chromium, and titanium. According to this chart, this is going to identify the different chemical compositions and what adding alloys they are adding to the metal. They add different materials like carbon, manganese, silicon, phosphorus, sulfur, nickel, chromium, molybdenum, vanadium, titanium, zirconium, copper, and aluminum. Then for stainless, we're going to have ER308L, which is going to be the same for ER. It's going to be electro rod. And then the 308 is going to reflect the grade of stainless that for the electrode filler. And the L is going to indicate that it is a low carbon electrode. And then for aluminum, we have ER4043, which the 4 is going to identify the series of aluminum which that this filler rod comes from, which is going to be the 4000 series. And then the 043 at the end is going to be the silicon content of that electrode. Common sizes for these electrodes that you're able to buy in the store are going to be 0.030, 0.035, and 0.045.
Alright, so up next we have Gmaw principles. Gmaw, gas metal arc welding, also referred to as metal inert gas, or MIG, is a welding process that forms an electric arc between a consumable MIG electrode and the workpiece metal, causing them to fuse. It's a wire electrode that's fed using a shielding gas through the welding gun, which helps prevent from atmospheric contamination. So the Gmaw welding process works on the following principles. The arc is struck between the workpiece and the metal wire electrode, and it's continuously fed. Then the wire is supplied on a reel and is fed into the welding gun by the drive rollers. Next, the contact tube is in the welding gun passes electrical energy from the arc to the electrode, and then thus resulting in striking the arc to complete the circuit. So here's a small chart detailing the differences between Fcaw and MIG. It's pretty big differences between the two of them. Fluxcore produces slag and spatter, and with MIG you shouldn't have very much spatter or slag, and it's the easiest type of welding process to learn. MIG is better for indoor. Fluxcore can be taken outside into the field and used in different conditions. Fluxcore is better for thicker materials, and Gmaw or MIG usually puts off a better appearance. And a big difference is Fluxcore uses internal shielding and MIG uses external shielding. So a major difference that separates the two processes is the electrodes. Fluxcore uses wire combined with flux, which will end up producing slag, results in more cleanup, while MIG uses a solid wire along with shielding gas instead of flux. With Fluxcore, you'll most of the time be using a dragging or a backhand method, and due to the slag, and MIG usually uses a pushing forehand method. Once again, a principle of MIG is consumable electrode, forms the heat between the metals, results in weld joints, and then MIG is a lot of times used for non-ferrous materials such as aluminum and different steels. Here's a video example.
Hey Kevin, what are you doing?
Oh, just hooking this longevity MIG Weld 140 back up for Fluxcore. I was going to do a little bit of welding. I've had a lot of questions here lately, the differences between Fluxcore and solid core. What the heck is it? What does it look like? Why do I need it? Okay, let's talk about it just a little. So, Fluxcore wire, metal wire with the flux impregnated right into the wire. So it basically replaces the stick electrodes that you would use with arc welding or stick welding.
So this is arc welding or this is MIG welding?
It's just, gets kind of blurry here. It's basically the same as arc welding, except that you have a continuous spool, which of course makes it MIG welding. But you're using no gas, at least with this type of wire. There is some Fluxcore wire that does use gas, but I just don't have any here. So, the benefits, it's quick, it's easy. You could put it in the machine and take it outside. The wind doesn't bother it. It's just like using a regular stick welder in that regard. With the different size spools, of course, you can weld for a very long time. You get a bigger spool of it. Rather than having to change your electrodes every time when you burn them out with a regular stick welder. Smoky, the downside, smoky, a little splatter, a little mess, just like an arc welder. Something you have to go back and clean up. You have to chip the slag off, just like with an arc welder. Where if you were running the solid core wire with the inert gas, you don't have any of that. There's a lot less smoke, a lot less things to clean up, a lot cleaner weld, in my opinion, a little better looking weld with the solid core over the flux core.
How about cost? Do you think it's a little cheaper to have the flux core instead of having to have the gas?
I think it's kind of a wash. I believe the flux core wire is actually a little more expensive for the same size spool as the solid core. But that expense for the flux core, you make up on the other side, or you lose on the other side, because now you have to buy the gas. So I'm making one of my railroad spike sculptures, and like I say, we're using that longevity MIG Weld 140. It's got the 035 flux core in it, and the the wire feed is set at 40 and the bolts are set at 9 on the dial. So slip your helmet on. We'll make a couple welds here and you can see what you get. So right there, without even brushing it off or anything, you can see the amount of smoke. And then, of course, you have to come back and knock your slag off and get your slag out of the way also. Just for the heck of it, let me fire up the other machine and we'll do a solid core weld on the backside. So that was
some disadvantages of MIG. The use of argon-based shielding gas for axial spray and pulse transfer modes is costlier. MIG is best used for flat and horizontal welding positions with higher heat input mode from axial spray. The welding type is limited to thinner materials due to the lower heat and short circuiting mode. It's less suited for fixed structural welding or heavy duty projects. You have to be in a particular controlled environment for MIG. And it usually requires the base metal to be clean prior to welding. So what separates MIG from other processes? A lot. In MIG, it uses the electrode that is constantly fed, and it just keeps going and you can use it for longer stretches without having to stop as much and replace electrodes or change out different consumables. MIG is the most widely used process, mostly because it's lower cost and lower cost consumables, while it offers higher deposition rates, especially compared to stick. Also with MIG, since it's a slagless process, doesn't require any chipping or cleaning up flux, discarding any used electrodes. So it allows for more time welding, less time wasted by all the cleanup and switching out different consumables. And another benefit is it's a pretty low skill level required to operate a MIG torch. The welding process is easily automated, and it's an ultra low hydrogen process. Also with MIG, it's used for many different metals such as aluminum, copper, stainless, mild steel, magnesium, nickel, and a few others. It offers a faster welding speed and increase in the quality of the welds. So next we have welding aluminum with MIG. So a few equipment differences when using MIG on aluminum. You have to consider the thickness. It's usually best to weld on a 14 gauge or heavier aluminum. If you're gonna weld on thinner than 14 gauge, you'll probably have to use specialized pulse setting. And with all processes welding on aluminum, you need to make sure it's cleaned prior, remove any grease or dirt from the material, and also any oxide using a wire brush, acetone. And also with aluminum, since it's a non-ferrous metal, it requires 100% argon compared to a 75-25. So your flow rate should be set accordingly. A few more equipment differences. When welding on aluminum, probably the biggest difference is you're using spray transfer. So it's a smooth transfer of molten metal droplets from the end of the electrode to the molten pool. The droplets that are crossing to the molten pool are usually smaller in diameter than the electrode. It doesn't use short circuiting in spray transfer. The deposition rate and efficiency are relatively high, but be aware that it does involve a high amount of heat, creating a larger pool with good penetration, but it could result in being more difficult to control. So try to avoid using that on thinner materials at 14 gauge. Also, another difference is your wire feeding options. When using aluminum, the wire is a lot softer, so you're gonna have to have a special liner, and it's usually used with a spool gun and a push-pull system. So spool guns make it easier to feed the soft wires, and spool guns usually eliminate the possibility of bird nesting because it's only feeding a few inches instead of through a whole liner. Also, with aluminum, you want to be using the right filler metal. Make sure you're aware of the base aluminum that you're going to be welding on, and then from there you can decide on which filler wire you're going to use. Most of the time it'll be 4043 or 5356, and you just decide from there. So a few techniques for welding on aluminum with MIG. You want to use a 10 to 15 degree push angle, push not drag, and tip and nozzle pointed in the direction of the travel. Using a drag will result in dirty and porous welds because of lack of gas cover. So maintain the proper work, the tip to work distance, and you want to have the contact tip approximately an 1/8 inch inside of the nozzle if possible. And that's mostly due to that it's very hot when welding aluminum, so if your contact tip is too close, it could lead to wire burning back, or you could run into feeding problems. With aluminum, you want to avoid large weave beads. If you need a larger fillet weld put in.
So my topic was name a welding process that is becoming prevalent in the welding industry, and I chose to do my PowerPoint on micro welding. So, what is micro welding? Well, it's literally exactly what it sounds like. It's welding, but it's on a very small scale, and there's 4 different types of micro welding. There's micro laser welding, flash micro welding, TIG micro welding, and micro resistance welding. It's mostly used for fusion welds, but you can also do it with filler as well. So here's the different types of micro welding. The micro laser welding is a technique that is a laser driven creating a fusion weld. The lack of gas that is there is so it doesn't contaminate the material. The flash micro welding is typically used to create clean joints using high pressure. In this technique, 2 metal components are joined by getting pressed together tightly and slowly at a specific temperature. TIG micro welding is literally exactly what it sounds like. It's just TIG, but on a really small and precise scale. And then micro resistance welding is literally like spot welds and seam welds. It just fuses the metal together
between the electrodes, kind of like yeah, literally like a spot weld machine, where you just hold the plate in between the two electrodes, and then it just melts them together. So where are these different applications used? Well, it's used for wires and foils, honeycomb welding, sensitive electronics, hermetic sealing of foils using the micro-resistant seam welding, small electronic and mechanical components, lighting components, battery tabs, sensors, motor connections, miniaturized components, and then even in some things that are heat sensitive and can only take a little bit of heat. And I also know that they use it for rings as well. And here is a video, an example of that.
Micro welding. And here is another welding method. Its distinguishing feature is the reduced beam diameter, which makes it possible to work with even the smallest details. The principle of operation, however, remains the same. It can be described as follows. Special equipment creates laser radiation, which is then focused into a beam. When it hits the parts to be welded, part of the beam is reflected, and the other part penetrates the metal. Heat absorption causes the metal to heat up and then melt. This is how the weld is formed.
Alright, there's a couple examples of it on there. And then
shielding gases used for MIG and flux core, and why. How to choose a shielding gas. So there are factors that will determine what shielding gas to use. The type of material is probably going to be the #1 reason for what gas you choose and or what ratio of gases. Filler metal can also be a reason, but that usually is determined off of the base material. As long as you're not using metals that cannot adhere to each other, you should be fine. Lastly, weld transfer mode can determine the gas type, whether it's a globular or a spray transfer mode. Material type. As I said earlier, this is most likely going to be the biggest factor for what shielding gas you choose. Carbon steel and aluminum are almost completely different when it comes to welding, so choosing the appropriate shielding gas would give you the best results. Material thickness can also be a factor when looking for a deeper penetration weld. Filler metal type. In order to weld anything correctly, the filler metal needs to match the base metal. So knowing what gas to use for the base metal will most likely put you in the ballpark for what the best gas is. Most WPSs will also say what gases to use with the required fillers as well. So here I have 3 different types of metals and their options for gas. Up top I have aluminum. 100% argon can be used. A helium argon mix also can be used for a deeper penetration or a faster travel speed, but do not use oxygen or like 100% oxygen or a CO2 mixture, because it will add a layer of oxidation and it runs very hot. Here I have a 75-25 mix of argon and CO2. This is not what you should use. So when I say combinations or ratios, even having that little bit, say 25% of CO2, it will cause that weld to run even hotter than it already does. And aluminum already uses such high amperage, it just will not work. Mild steel, you can use 100% CO2 or even the 75-25 mixture. If you want the deeper penetration, you can use a CO2 oxygen mix. As the material gets thicker, adding oxygen to gas will help with the penetration. And then carbon steel is pretty simple as well. You can use 100% CO2 like this here. This is what this will look like. I'll just say carbon dioxide, non-flammable gas. So you can use 100%, you can use the ratios. People will have differences, 50-50, 75-25, 100%. Mild steel and carbon steel aren't too far apart with the ratios. It's just more of a preference or what the WPS says it requires, the filler metal. But other than that, it's really not too far apart. So now we have flux core and the gas types that are used for this process. Flux core being a very versatile welding process, choosing the correct shielding gas is a must when using it. Flux core is mainly used for heavy industrial work and structural work, so the gas options are pretty simple. On the bottom here, it says the two most common shielding gases used for flux core are 100% CO2 and a binary blend of 75% argon and 25% CO2. So like before with the mild and carbon steel, you can use the 100% CO2, and as we know from now using flux core, it runs very, very hot. So even whatever mixture you go with, it will still get pretty good penetration. But if you need to step it up for very thick pieces of metal, like the heavy industrial stuff that I said, using the 100% CO2 will allow it to get full penetration with whatever wire feed speed and voltage you use. And then the mixture you can use for smaller stuff, and it can allow the different travel speeds, and a lot of it can come down to personal preference for the job. And like I said earlier, the WPS. There is self-shielded flux core. The flux inside the filler wire produces its own protective layer of gas while welding. The flux in the wire melts when heated, and in turn produces gas, which then counterbalances the weld pool. Self-shielded flux core is a very economical welding process since you don't have to spend the extra money on welding gas.
Fcaw electrodes and the classification system for it by me. Let's see how to classify these. The Fcaw electrode classification. This is a classification chart right here, kind of like stick welding. We have an electrode here, minimum tensile strength, second one, welding position, tubular electrodes, that one, usability, shielding gas type, improved toughness, supplemental mechanical property requirements, that's this one, and diffusible hydrogen levels is right there. Okay, so look at some of the types, different types of Fcaw electrodes. So Fcaw electrodes are these types right here, are designed for the use of one specific type of shielding gas, which is ultra-core 71C and ultra-core 71A85. Fcaw electrodes designed for higher strength steels are these right here, ultra-core 81, outer shield 91, outer shield 690. And HD type Fcaw electrodes are designed for high deposition, out of position capability, right here. And these right here, exceptionally high deposition rates in the flat and horizontal position. These two right here. And let's see, these ones right here are for improved lower temperature toughness properties. That's it, these two right here. And here's a good picture kind of demonstrating how Fcaw works. Okay, let's look at some different types of Fcaw electrodes. Mainly there's going to be two types that are going to be used in the welding industry, E71T-11 and E71T-8. So these wires are versatile options for structural applications and are both suited for all position general purpose welding. And both of these wires should be ran on DCEN in contrast to that of Fcaw, which is ran on DCEP. So these wires should also be stored in its original packaging in a dry environment to prevent moisture pickup, which will cause lots of problems running these wires. As we saw like last week ago, it wasn't running right. Let's continue on. And there's another good picture right here. Get out of the way. Here's a good video, kind of demonstrating the advantages and disadvantages of it. I'm not going to play the video, but I'll play a little bit of subtitles, but it's basically just subtitles. But he's basically explaining the advantages and disadvantages of Fluxcore G and Fcaw self-shielded. We can skip ahead a little bit. All right, there we go. So let's take a look at some advantages of Fcaw gas shielded or dual shield. It's less spatter, easier slag removal, smooth bead appearance right here. Looks really nice. Deep penetration, it's a very fluid puddle, easily wets in. Less smoke compared to self-shield as well. And let's look at some of the disadvantages of it. You must use gas with it, so it's less borable due to that fact. Must be used in an area with no wind or very little, otherwise you're going to get porosity. And right there. It's more expensive due to the gas associated with it, so more expensive. Let's continue on. Advantages of Fcaw self-shielded. It's very portable, you don't need gas with it. It can be used in windy environments. It's less expensive, so it's a big upside. Some disadvantages of self-shielded. It's lots of spatter, lots of smoke. It's less appealing to look. Less appealing look to the weld profile. It's harder slag removal, and it must be kept stored in a dry environment when not using to prevent moisture from building up in it. And it's more susceptible to worm tracking than dual shield. Right, and in conclusion, these two processes are very similar, but also very different in a lot of ways. From technique, gas cost, portability, wind conditions, spatter, bead profile, etc. What I would say for which one to pick is to evaluate the advantages and disadvantages of each one and to pick which one is right for you. There's my works cited page.
This is a presentation on Gmaw transfer modes. Transfer modes for MIG welding play an important role in the level of quality and productivity that can be gained in a welding operation. The modes are influenced by the power source, welding parameters, and shielding gas. They also have an impact on the weldability of the welding wire, or in other terms, its ease of use, arc performance, and bead appearance. There's 4 types of transfers. You have globular transfer, short-circuiting transfer, axial spray transfer, and pulse spray transfer. The globular transfer operates between short-circuiting and spray transfer. Large droplets, irregular in shape, but larger than the wire diameter, transfer across the arc into the weld pool. The transfer occurs at higher wire feed speeds and voltages than short circuit transfers. Increases productivity, but the mode tends to generate spatter that will need to be removed. Maybe quite a task to remove the spatter. This transfer mode pairs with shielded flux cord welding using 100% CO2. It makes it relatively inexpensive, and it can be used to weld 1/8" base materials or thicker. I don't know if it's gonna let me watch this video or not. We'll come back to this. Spray transfer. Operators often cite the appeal of spray transfer mode as being quite high, since it's easy, smooth, and it's a stable arc and welds faster than other transfer modes. As the name implies, the spray mode generates a spray of tiny droplets, smaller than the wire diameter. Increases deposition rates, provides good fusion and penetration, and creates little spatter, so not as much spatter to clean up. The weld bead is also aesthetically nicer. Spray transfer mode operates at a fairly high amperage and voltage, so it's capable of higher levels of productivity. When you pair the process with a metal cord wire for flat and horizontal welding, it can increase the productivity further due to the ability to achieve fast travel speeds and minimize spatter. Generally, the spray transfer mode is used on material 1/8" and thicker and is suited to carbon steel and aluminum. It operates at relatively high voltages with 80% argon and 20% CO2. There's not a whole lot of risk of undercut. Undercut can occur if the arc becomes too long. Short circuit transfer. During this transfer, the welding wire touches the base material, creating a short from the electrical contact that transfers the weld to the joint. The short circuiting occurs between 90 and 200 times per second. This transfer mode operates at lower parameters, wire feed speed, and voltages. Generates lower deposition rates, making it a slower process than others. It's versatile for welding in all positions and on thinner metals. Metal cord wire could be used in this mode. For both wires, the mode can be used with a shielding gas mixture of roughly 75% argon and 25% CO2. Short circuit transfer mode can also be used to weld thicker materials, but because of its lower welding parameters, it can be prone to lack of fusion and penetration. Conversely, the lower heat input can help reduce distortion. This mode is prone to creating spatter depending on the thickness of the material, which may make it less appealing to operators and can increase post-welding cleanup time. And a pulsed spray transfer. Operators will notice a distinct sound difference compared to other modes. This is a result of the power source cycling between a high peak current or voltage and a low background current. The peak current pinches off a small droplet of wire and propels it towards the weld pool. The background current doesn't generate weld metal transfer. This cycle occurs between 30 and 400 times per second. It does require a higher skill set to weld aluminum in the pulse sprayed mode, but it's easier on other materials. The welding operator can gain good control over arc starts and stops. The operator has better control over weld bead appearance. And with the lower heat input, it reduces the opportunity for distortion. You get faster travel speeds and lower spatter levels than other modes. This, of course, supports productivity initiatives. When you pair this process with metal cord wire, it allows for welding out of position and gaining the benefits of this filler metal. High deposition rates, low spatter, and good gap bridging. It can be successfully paired with solid wires. The shield and gas mixtures for both may vary by the specific wire, but include 80% argon mixes. It typically requires a contact to work distance of 3/4 of an inch for the best performance and consistent results. In conclusion, knowing which filler metals should be used with each weld transfer mode and the advantages and limitations of each process can help welding operators gain consistent weld quality. Certain modes may be slower than others, but each has its place in any given welding operation. It's important to remember to use the different modes with the proper parameters and align them with the right application to gain the best results.
Okay, so this is all about FCAWS, or self-shielded flux cord arc welding. What is FCAWS? A lot of people don't know what this process is because of the S at the end of it, but basically the S is just there to show you or determine that it's self-shielded welding. So FCAWS is a type of flux cord welding that uses a flux core wire function as a consumable electrode. What this means is if you've ever stick welded before, then you know the flux that's covering the stick rod. While a lot of people think of the electrode used in this process as a, quote, stick electrode inside out. The shielding gas is from the flux within the electrode, so this type of flux core welding doesn't require an external welding gas, which makes it different from other flux welding. Problems that occur with this type of process is when you're welding, there's a lot of smoke made when using it, so it can be very difficult to see the weld pool, and this can happen easy when the machine settings aren't set up correctly. Another issue is slag inclusion. This happens easy as well because the particles of the flux become trapped in the weld, making full penetration very small to none. Porosity is also a very ongoing issue with this process. If you don't know what porosity is, it's basically just like small rounded holes in a welding bead, and they show up when gas gets trapped underneath the weld. This can happen easy because the gas from inside of the flux can get trapped in the middle of the bead. So when we talk about porosity, that moves kind of onto wormholes. So something that happens a lot with this type of welding is wormholes in the weld beads. What a wormhole is an elongated gas inclusion. So it's basically porosity just elongated. You can prevent this from happening is if you're keeping the wire electrode length a good distance from the contact tip, and also removing any dirty metal or any dirty things from the base metal, and that also does help with getting porosity. This is equipment setup. So this one looks like it's very good for mango aluminum, and also the wire goes right in there. Make sure you're putting the proper wire in is the first thing. Place the wire in guide tube, and then you put it past the rollers. When doing this, you want to make sure you're holding onto the wire as much as you can, because then the wire will start to untangle. Third, you want to pull down the spool brake to make sure the wire doesn't get tangled, because that's what holds the wire in place. And then fourth, you put the spool housing covers on, and with the spool housing covers are basically these covers that cover the important parts of the spool gun. And then after that, you want to slide on the gas diffuser, then you screw in the tip holder over the top of the diffuser. After doing that, you just want to press the gun to see if the wire goes through the tip holder. You would leave the wire showing a little bit and place the contact tip over the tip holder, and it can where the wire isn't coming out as it should. So when changing that, you take the nozzle off the MIG gun. You want to remove the contact tip and the diffuser. Third, you want to then lay the gun as straight as possible. You do this so that the liner just comes out as smoothly as it can. Fourth, after throwing away the old liner, you take the new liner, you feed it into the gun, then screw the liner back into position. And when you're feeding it to the gun, you just want to make sure you're doing it like slow and